Okay, reviewing for it says power quiz, but we actually have two quizzes. We have half of it is on energy alone. What are the different forms of energy due to, and how to use energy conservation, the before and after energies to solve for stuff. And then I have a separate quiz for the power, which is about the horsepower and the watts and the lifting of things up by pulleys and how much power is exerted. That's because in the past I've had them as two completely separate chapters, but I've combined them here so that time is better used. So anyway, that's why that's all about. Name the action, transformations, pros and cons of each power plant. So right now, think to yourself, what is happening in a coal plant in order to make electricity? What's the actions that I would see if I videotaped things going on in there? Think about that for a second. All right, and hopefully you said something like boiling water, steam turns a generator. So the energy transformations that are occurring there would be that we start off with the chemical energy that's in the bonds of the coal, and that turns into thermal energy as we burn it, and that thermal energy eventually gets turned into kinetic energy of the steam rushing through the pipes, and that kinetic energy is passed on to different items, and eventually it turns the magnets in the generator, and that makes the electric energy. The pros, think about the pros of coal. You should be thinking about how it's cheap and how it's very reliable. You can do it 24 hours a day. It doesn't require any fancy developments of technology. The cons, think about the cons right now. Mainly it's air pollution. I don't know of any other con. Anybody else know a con? Okay, nuclear power plants. Think about what's going on and what's the action. What goes on in a nuclear power plant to make electricity? Think about it, think about it, think about it. It's the exact same thing as a coal plant. The only difference is how do we get the heat to boil the water. In a nuclear power plant, it's the breaking of atoms. In the fuel rods, we'll learn exactly what's going on, but big atoms of uranium are breaking into smaller atoms. Okay, the transformations. It's going to be very similar to the coal plant here. One step is different. Think about what would be the one step that's different here. It's the first step. Where do we get the thermal energy to boil water? In a nuclear power plant, it's the nuclear bonds between protons. But everything else is the same. Pros. Think about the pros. No air pollution would be one of them. It's fully developed. We don't need any breakthroughs. That would be another one. You can make gobs of electricity this way. You can power an entire state this way. Cons. Think about that. The only one that I'm aware of is the waste. Wind turbines. The action there is just the blades turning the generator. Nothing else really. Very, very simple. Transformations. What is the energy transformation going on in a wind turbine? Think about it. Write it down if you can. just one step. The kinetic energy of the wind passing on to kinetic energy of the blades, kinetic energy of the axle, the gears, but you're spinning magnets, and that turns into electric energy. Pros and cons, think about those. Can you remember them? The pros is no air pollution, no fuel is needed. That's all grand. The cons, unfortunately, it's unreliable. Only when the wind blows. Right now, it's not economical. You cannot make a profit. Hydroelectric plants, what's going on there? Water turns a generator. The water flowing through special turbines, a fancy fan, so that it's optimal in terms of the forces and speeds and all of that, and that turns the magnets in a generator. So the transformation is the same thing as a wind turbine. The kinetic energy, I spelt that wrong. The kinetic energy of moving water gets turned eventually into the electric energy. The pros, no air pollution, no fuel needed. It's all fully developed. We know how to do it really well. You can make gobs of electricity this way and power an entire town. Cons, you can't do it everywhere, only special locations. And you destroy an environment. Instead of butterflies and squirrels, now you have fish and eels. Solar panels, what's going on there? We ran out of time when we were doing that lesson, but the light makes electrons jump between layers, jump between two layers. The solar panel actually has two layers of material, and the light makes the electrons jump across, and then they flow through the wires of your circuits to get back to their original spot. So the transformations there are very, very simple. Just simply light energy turns into electric energy. Pros, no fuel, no air pollution. Cons, unreliable. No, because I can put the solar panel in a dark oven and it doesn't make any electricity at all. So it's got to be the light energy. Okay, define energy. The ability to change things. Now that's pretty ambiguous. To change what? To change it in what way? Well, change just about anything, and in lots of different ways. You can change it by raising the temperature, changing the color, changing the consistency, changing the phase that's in, solid, liquid, or gas, all different kinds of changes. The unit of energy is the joule, Joule, or just simply capital J. Power is the rate of changing energy. Rate of changing energy. How fast do you add energy to something or take it away? The equation for power. Look up at the board. Can you see it? Can you see it? Can you see it? I have it up there. P is equal to delta E all over T. Now, whenever you see the delta, that means change in, and the standard way of finding the change is the final thing minus the initial thing. And the unit for that is going to be the watts, or horsepower. Does a horsepower have anything to do with a real horse? Yes, it does. According to some calculations way back a couple hundred years ago, they figured that 1 horsepower engine had the power of 1 horse. A teenager drops from a 4-meter high tree branch and lands on a trampoline. The person has a mass of 80 kilograms. The trampoline has a spring constant of 100. how much does the trampoline stretch? So we're going to use energy conservation in this case. That's the idea that the initial energy, when the person is in the tree branch, is going to equal the final energy, which is the stretched trampoline. We just have to figure out what kind of energies they have. Initially, when they are high up, that person is not... Whoop! What's up? Because hopefully the story problem will say use energy conservation. Let's see here. So initially, the person is not stretched at all. The trampoline is not really stretched at all. The person is not moving initially. The person is just high up. So that means they have gravitational energy, mgh. That's the initial on the left side. At the bottom, when the trampoline is stretched all the way, what kind of energy do they have? When they stretched all the way, they've come to a stop, so they have no kinetic energy. They are as low as possible. We don't know the height of them above the ground at this point, so we can't say anything about gravitational energy. So it must be elastic energy, 1/2 kx squared. So now we put in our numbers and we try to find out how much it stretches, which is going to be the x value right there. We put in numbers for everything else. The mass is 80, 9.8 for gravity, and the height was originally 4. On the right hand side, half the k is 100, and we're looking for the x. Getting the calculator out to do all this. 80 times 9.8 times 4. On the left-hand side is 3136. And then half of 100 is 50. So I got to divide both sides by 50. I get 62.72. But that is not my answer. You don't stretch a trampoline 62 meters. You got to square root both sides now. 7.9. Does that make sense? I hope you say, what? Stretching a trampoline 8 meters? That's ridiculous. And I agree with you, it is. So these numbers are all whacked out. A trampoline probably has a much higher spring constant than 100. But for these numbers, that's what it is. Number 12. A 200 Newton force pushes a 10 kilogram toy, so it speeds up from that to that in 4 seconds. How much power was exerted? So the equation for power is the change in energy divided by time. What kind of energy is changing right now? Think about that. We're speeding up. So we are changing kinetic energy. So, kinetic energy is 1/2 mv squared. That's the final minus the 1/2 mv squared initially. Remember, it's the final minus the initial. Divide by the time. Put in our numbers. 1/2 times 10 times the final velocity 3 squared minus 1/2 m the initial velocity squared. And we divide that by the time of 4 seconds. 1/2 times 10 times 3 squared minus 1/2 times 10 times 1 squared equals 40. Divided by 4 is 10. That does not look familiar from this morning. Let me double check this. Somebody else got it too? Okay. Let's see, this is 5 times 9, that's 45, and that's 5, 40. Yep, I guess that is right. Okay, the next one's tricky. Chocolate bar to somebody who comes up with the answer. Let me get my chocolate bars. I have Hershey's, I have Reese's, I have Kit Kats, I have Skittles. Who can come up with the answer? The last problem at the bottom. It's a number. 7. No.
9.8.
No.
0.
0 is correct. Kit Kat or Reese's? Kit Kat. Now, I highly suspect, forgive me if I'm wrong, I highly suspect that he was just guessing. That's fine. But he had the guts to make his guesses verbal. So, yes, the power is 0. Power is delta E over T, and he said that was 0. Is the time 0? No. Is the time infinity? No. So how can we get a 0 out of putting in 20 seconds here? The top has to be 0. Why would the delta E be 0? It's stationary, so it's not having any kinetic energy whatsoever. The ending kinetic energy is the same as the beginning. 0, 0, 0, 0, all around 0. Are we raising it up to be a higher gravitational energy? No. Are we stretching it to store up elastic energy? No. So we are not adding any energy to the object, therefore there's no delta E, there's no power. Alrighty. Yes. Yep. Alright, that's the end of that.